One other important application of integration is using integrals to calculate probabilities. We're going to open up with what is called a discrete probability distribution. Discrete meaning distinct. Let's suppose we roll two six-sided dice, and then we're going to find the sum of the values on those two dice. Of course, the minimum value we can get is a 2 with a 1 and a 1, and the maximum being 6 plus 6, which is 12. However, not each of these will be equally likely. And so what I have here is this nice little sort of triangular distribution of the different sums. Here we would have a sum of 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And what I've done is I've listed out the combinations that will get you there. Now you might want to be careful here because some people will say, well, isn't 2, 5 and 5, 2 the same? Well, it's the same sum. We use the commutative property, but imagine yourself having two dice, a red die and a green die. Well, you could have the red die be 1 and the green die be 5, for example, or you could have the red die be 5 and the green one be 1, which will give that sum in two different ways. So we could ask the question, what is the probability that I roll a 9? And the way we denote this is we denote it by, say, P of 9. Or sometimes we'll even do something kind of crazy, Px equals 9. X is what we call a random variable, which is a variable whose outcome is determined by some sort of random event. Well, the probability that we end up with a sum of 9 would be, well, there are 4 different outcomes here that would do that. 1, 2, 3, 4, out of the total number of outcomes, which is 36. So when you reduce, there is a 1 in 9 probability of rolling a sum equal to 9, or yes, equal to 9. Now, what does this have to do with integration? Well, I would like to imagine that these stacks are, each little stack is 1 unit wide. And then here's the funny part. Because each outcome is 1 out of 36 outcomes, the height of these, even though I have tried to draw them as squares, is only 1/36 of a unit high. The probability that we end up with a roll of 9 is then, well, the area of that particular region. On the other hand, if I say, what is the probability that my roll is, let's say, between 9 and 7, we would have the area all the way to here. And so we would want to figure out that whole area, which is, well, if we count the squares, there are 15 squares, so that would be 15 out of 36, which reduces to 5/12. There are a few important takeaways from this particular example. First of all, one of the takeaways that is important is that the area we can think of in terms of the probabilities. That's particularly important. Another one is that the probabilities are always positive. Well, not positive. They may be non-negative, we should say. Why do I say that? What's the probability that the sum of these two dice will be equal to 82? Well, of course, that probability is 0. So the probabilities could be 0. And the other thing is that when I find the sum of all the probabilities, we get 100%, which we don't really like to use. We like just to say 1. So the total area under this region would be 1. That means that the integral is going to be 1. So here we have the continuous version of this. A function f of x is a probability density function. First of all, it has to be a non-negative function. The function values always have to be greater than or equal to 0. The sum of all of the probabilities has to be 1. While sums are the discrete version, integrals are the continuous version. So the integral from negative infinity to infinity has to equal 1. That may seem intimidating because it is an improper integral. Many times, however, the probabilities will be defined to be 0 outside of a particular range of numbers. To denote the probability that we have a continuous random variable x that lies between a and b, we write the probability that x is between a and b, and it's going to equal the integral from a to b. So let's look at the picture here. Over here in this picture, the area bounded by the curve and the x-axis is going to have a total equal to 1. That total area is going to be 1. It's going to be all above the x-axis because probabilities are always positive. And when we want to find the area or the probability it's between two values, we will do the integral from a to b. Let's look at our first example. Here we have a function that is piecewise defined. These sometimes confuse students. So I like to read them backwards. I like to say, hey, f of x is equal to, wait a minute, if x is between 0 and 1, we're going to use this particular rule. If x is not between 0 and 1, if it's something else, we'll call it 0. So the probability, or f of 5 would be 0. F of negative 2 would be 0. F of 0.5, well, we don't have enough information because we don't know the value of k. So we want to know for which value of k is it a probability density function. And here's the key to answer this question. We need to have that the integral from negative infinity to infinity of my function be equal to 1. Okay? Well, it's not quite that bad because our function is only defined from 0 to 1, so we want this integral to be equal to 1. We can pull the k out and then take the antiderivative of x squared and x to the fourth. We'll get 1/3 x cubed minus 1/5 x to the fifth. We're going to evaluate this between 0 and 1. It should be equal to 1. When x is 0, x cubed and x to the fifth will equal 0. When x is equal to 1, both of them will equal 1. So we end up with the equation that k times 1/3 minus 1/5 equals 1. Well, 1/3 minus 1/5 is 2/15. K equals 1, which means that k is 15/2. So the value that will give us a probability density function is the same value that will give us an area equal to 1, and in our case it's 15/2. So for part B, we want the probability that whatever this random event is, that the outcome is between 1/2 and 1. And for that we use integrals. We now substitute our value of k in. So our k, I'll just keep it out front, is 15/2. We're going to do the integral from 1/2 to 1 because those are the boundaries for what our random variable x is. And then we'll have x squared minus x to the fourth. One thing that you'll find with these problems is that you'll often do the same integral repeatedly. So we end up with 15/2 of 1/3 x cubed minus 1/5 x to the fifth. We're going to evaluate this from 1/2 to 1. Once we work this all out, we get 47/64 as our probability. Again, pause this and check out the calculations if you want to work through them on your own. For our next example, I'm going to do a little sort of example to help illustrate this. We're going to talk about what are called average values or mean values. Sometimes it's called the expected value. So let's pretend we have a game, and in this game, we're going to roll a 6-sided die. If we roll a 1, 2, or 3, we win $1. If we roll a 4 or a 5, we win $2. And if we roll a 6, we win $5 whole. The question is, how much would we be willing to pay to play this game. Why will we even consider it? Well, I'm always going to win at least $1. So certainly if it only costs me $1, it's worth playing. If it costs me $5, that's definitely not worth playing. At some place, there's a breaking point. And here's the way you can look at this. Out of the 6 outcomes, 1, 2, and 3 will win me $1. So that means half the time I will win $1. 4 or a 5, 2 out of the 6 times, or 1/3 of the time, will win $2. And 1 out of the 6 times, 1/6 of the time, we win $5. If you add this all up, we end up, we're going to put a common denominator of 6. We have 3, and then 4, and then 5 of them. We end up with 12/6, which reduces to 2. So $2 is our sort of break-even point. If we're playing at $2 every time, on average, we won't lose money, we won't gain money. On average, we will definitely lose and gain money, but our overall winnings will stay right around 0. This is what's known as the expected value. How much do we expect to make on this? Well, what did we do here? Well, the first thing we did was we looked at the probability that we win $1. We'll use X as the random variable, what our outcomes are. And then we multiplied that by the outcome. What is the probability that our winnings are $2? Now, we multiplied that by 2. What are the probabilities that my winnings are $5? We multiplied that by 5. So what we're doing here is we're finding the sum of these probabilities and then multiplying them by the outcomes. And that's precisely what we'll do with integration. Our probability density function is this f of x. The outcome is x. So in order to find the average value or the mean value or the expected value, we're going to take our function and multiply it by x. Okay, this actually is very similar to what we did with the centroids. This is essentially the moment about the y-axis with a density equal to 1. The density being equal to 1 is because the average value or the total integral of a probability density function equals 1. Now let's do this. Let's find the average, expected, mean value, whatever you want to call it, for the function that we were playing with before. Remember, it was f of x equals 15/2 of x squared minus x to the 4th when x was between 0 and 1. According to our definition here, it's more of a rule, but it's a definition, the mean value is going to be equal to the integral from 0 to 1, x multiplied by that function, 15/2 of x squared minus x to the 4th dx. Now we'll do a little simplification here. Let's pull out the 15/2 in front of the integral and then distribute the x to both terms there. We'll end up with x cubed minus x to the 5th. We'll find the antiderivative and compute the values at 1 and 0. When we find the antiderivative and substitute 0 and 1 in, when x is equal to 1, we'll get 1. And when x is equal to 0, we get 0. So our expected value is 5/8. Again, what does this mean? Our function from 0 to 1 looks something like this-ish. The mean value is sort of a left to right balancing point for this particular region. So I'm going to guess it's somewhere, well, 5/8 is right about there. So that would be the balancing point left to right. One common problem that we face when we're doing probabilities is wait times. Suppose we are at some sort of store and we want to know what's the probability that we're waiting in line no longer than 5 minutes. This might also apply to voting. You're at the polls, how long will you have to wait, how long will you have to wait when you're online. And it's all related to the average value, okay? At least for our particular model. We can use wait times and integrals together if I want to know what the probability is that I wait between 0 and 5 minutes, it'll be the integral from 0 to 5 for some function f of x. There are lots of different functions that we can use. The most common choice, or a common choice, is the following. That, well, we might walk in and there's no line at all, in which case we wait 0 minutes. We can't wait negative minutes, so if the time we have to wait is less than 0, we're going to assign 0 to that probability or that particular function value. When t is greater than or equal to 0, we're going to assign the probability of 1 over mu e to the negative t over mu. I prefer to look at it like I said rather than that's written, 1 over mu, mu being the mean value, e to the negative t divided by mu. So these are common choices when we're dealing with wait times. Now mu is the mean wait time. What do I mean by that? Well, let's suppose we are at some particular store and we watch and somebody comes in, we start the stopwatch. Oh, they had to wait 3.5 minutes. The person behind them had to wait 3 minutes and 50 seconds. The person behind them had to wait 2 minutes and 52 seconds. So we're going to take all of those values and find the mean value. That's where that mu comes from. So let's look at an example of this. The average wait time at some polling location is 7 minutes. What's the probability that someone waits fewer than 4 minutes? Well, it's just as we would expect. Our mu here is 7. We're going to use the formula we just came up with. Mu is equal to 7. And remember, it was 1 over mu e to the negative t divided by mu. In order to get the probability that we wait fewer than 4 minutes, we would say, well, the probability that x is between 0 and 4 is going to be the integral from 0 to 4 of 1/7 e to the negative t over 7 dt. Okay? Well, the 1/7 will come out front when we find the antiderivative. When we do find the antiderivative, the exponent is a linear function, negative 1/7 t. So if the negative 1/7 was not there, let's pretend it's not there, the antiderivative of e to the t would be e to the t. So because it's a linear exponent, we can kind of guess what the antiderivative will be. And it turns out to be negative, well, hang on to the negative for a moment there. We'll say e to the negative t over 7. And then we're going to multiply by the reciprocal of negative 1/7, which is going to be negative 7. Now let's check ourselves as we do this. If I take the derivative of this expression inside the parentheses, it would be negative 7 multiplied by the derivative of e to anything is the exact same thing, multiplied by the derivative of the exponent. Well, the exponent is negative 1/7 t, so the derivative would be negative 1/7. The negative 7 would cancel with the negative 1/7. So this is the correct antiderivative. We're going to evaluate this between 0 and 4. Again, be extraordinarily careful. When t is equal to 0, we do not get 0 this time. So the 7 and the 1/7 will reduce. We still have the negative there. So we'll end up with negative e to the negative 4/7 minus negative, so plus e to the negative 0 over 7. Well, that's equal to 1. So we end up with 1 minus e to the negative 4/7. That is approximately equal to about 0.4353, if you want a decimal approximation. Okay. Now, let's suppose somebody is in an extreme hurry. What is the probability that someone waits at least 10 minutes? At least 10 minutes. Well, in our notation, that would be the probability that x is greater than or equal to 10. Okay, so hit the pause button here. Not really on the video, but let's think about this for a second. Let's suppose somebody tells us what it is. Suppose somebody tells us the probability that you wait at least 10 minutes is 25% chance. Well, then what's the probability we wait less than 10 minutes? Because that's what we're really hoping for. Oh, that would be 75% chance. We took 100% minus the probability that we waited more than 10 minutes. Well, let's flip that around. Let's suppose somebody tells us that the probability we wait less than 10 minutes is 60%. What's the probability we wait more than 10 minutes? Oh, well, that would be 40%. Again, 100% minus 60%. 1 minus 0.6. So this is going to be equal to 1 minus the probability that we wait between 0 and 10 minutes. Now you might say, why was he doing that? Why does that even matter? Well, it matters because this is equal to the integral from 10 to infinity of 1/7 e to the negative t over 7 dt. Blah. An improper integral. We don't like those. Instead, this one is 1 minus the integral from 0 to 10 of 1/7 e to the negative t over 7. Ah, that's much better. It's not an improper integral. So we end up with 1 minus, we've already done the antiderivative. It is negative e to the negative negative t over 7. We're going to evaluate this from 0 to 10. So we end up with 1 minus, okay, when t is equal to 10, we'll end up with negative e to the negative 10/7 minus a negative, so plus e to the 0th. Okay, e to the 0th is 1, and we'll have this 1 out in front minus this 1 inside, and so it turns out to be just e to the 10 divided by 7. That should say negative 10 over 7, which is approximately equal to 0.22397. When you take a collection of scores and line them up, the score in the middle is what's known as the median score. The median will be the place where half of the scores are less than that and half of the scores are greater than that. That's true whether we're dealing with a discrete probability density function like rolling dice, or a discrete collection of data like exams, the number of students in an exam, or if I'm dealing with continuous information. So the median wait time in this particular case would be the time at which exactly half of the people wait less than that time and exactly half of the people wait more than that time. And so I'm going to let m be the median wait time. So half of the people will wait between 0 and m minutes. What's the probability then that I wait between 0 and m minutes? It will be the integral from 0 to m of 1/7 e to the negative t over 7 dt. Now, I could have, and I'm going to write this over here, said it's the integral from m to infinity of 1/7 e to the negative t over 7 dt. But then I'm dealing with an improper integral, and I don't really like to do those. So this should be equal to 1/2, as should the improper integral. So we'll go ahead and evaluate the integral. We've already done it a few times. We'll go ahead and evaluate the integral and then solve for m. If you evaluate the integral, we ended up with negative e to the negative t over 7, evaluated from 0 to m. I will do this calculation and then set it equal to 1/2. Let's see, that would be negative e to the negative m over 7 minus negative, so plus e to the 0th, which is 1. And we want this equal to 1/2. So this is the equation that we now need to solve. We need to solve this for m. Well, we could subtract 1/2 from both sides. If we do that, we'll end up with negative e to the negative m over 7 is 1/2 minus 1, which is negative 1/2. Multiply both sides by negative 1. We'll end up with e to the negative m over 7 is equal to positive 1/2. Our logarithms will help us out here. If you take the natural log of both sides, you get negative m divided by 7 is the natural log of 1/2, which means that the median wait time is negative 7 times the natural log of 1/2, which is approximately equal to 0.485. That's incorrect. Not 0.485, but 4.852 minutes. Okay, that's the median wait time. So half of the people will wait less than that, half will wait more. But remember, the mean wait time was 7. The median is less than that because somebody could potentially wait 20, 30, 40, 50 minutes. And the larger values you get there, the larger the mean is going to be compared to the median. For our next example, we're just dealing with another probability density function. Here we have the function 1/18 radical 9 minus x when x is between 0 and 9, and the function will be 0 in other places, anywhere else. We want to show that it's a probability density function. Again, in order to be a probability density function, we should obtain 1 when we find the integral. Our integral is going to go from 0 to 9, technically from negative infinity to infinity, but the exciting places are for values between 0 and 9. And then we take the antiderivative of 1/18 times the square root of 9 minus x dx. Okay, we'll go ahead and make a substitution here. So let's let u be equal to 9 minus x. du is negative 1 dx. And so since I don't have a negative, we'll say the opposite of du is dx. Now I'm a huge fan of switching limits when I have a substitution problem. So we're told that x starts at 0. When x is 0, u is 9 minus 0, which is 9. And then we're told that x ends at 9. And so when x is 9, u will be 9 minus 9, which is 0. Let's put this all together. We end up with, from our substitution, dx is the opposite of du. So I'm going to bring the negative out front. Du I'll put back here. Now here's the weird thing. When x was 0, that's the lower limit, u is 9. So my lower limit is going to be 9. When x was 9, u was equal to 0. So my upper limit will be 0. It does not feel good to have smaller numbers as the upper limit, but that's the case. And then the 1/18 I'll keep in there. And then it's u to the 1/2 power because it was the square root of 9 minus x. 9 minus x is u. Kind of crammed in there, sorry about that. So we end up with, when we do the antiderivative, negative 1/18. U is to the 1/2 power, so its new exponent will be 3/2. And then we need to multiply by 2/3 to compensate for the exponent of 3/2. This is going to be evaluated from 9 to 0. Another way you can justify the unsettling feeling of having the larger number on the bottom here is the fact that if I were to interchange those two, it would switch the sign back to a positive out front. So it's okay. When u is 0, we don't need to resubstitute. We shouldn't resubstitute. Also, I'm going to go ahead and do the 2 divided by the 18. Well, 18 divided by 2 is 9. We'll have a 9 in the denominator. Combined with that 3 will give us 27. So negative 1/27. When u is equal to the upper limits, that's the 0, we'll end up with 0 to the 3/2. And then we subtract negative 1/27, so plus 1/27 times 9 to the 3/2. Well, let's think about this guy is going to be 0. And 9 to the 3/2 means we're going to take the square root of 9, which is 3. And then we raise 3 to the 3rd power, which is 27. So we end up with 1/27 of 27, which is 1, which is what we expected. We wanted it to be a probability density function. It has to equal 1. Now let's find the probability that x that whatever event we have here is between 5 and 8. And it's a pretty straightforward thing. We just do the integral from 5 to 8 of 1/18 times the square root of 9 minus x dx. We've already done this. We did it by substitution. We said u is going to be 9 minus x, du is negative dx, so the opposite of du is dx. Here our limits are a little bit different. If x is equal to 5, u is, u is 9 minus 5, which is 4. That's convenient. You'll see why. If x is equal to 8, the upper limit, u is 9 minus 8. Again, 1, which is nice because it's a perfect square. So let's go ahead and make the substitutions. We end up with the opposite of 1/18. Instead of going from 5 to 8, from 5 to 8, we're going to go from 4 to 1. So integral from 4 to 1. We have the 1/18 pulled out front, and this is u to the 1/2 du. The negative is there associated with the dx. It's out front. And so we end up with negative 1/18. Again, this will be multiplied by 2/3 because it's u to the 3/2 from 4 to 1. When u is 1, we end up with negative 1/27, calculation from the previous slide, times 1 to the 3/2 minus, or actually minus a negative, so it'll be plus 1/27 times 4 to the 3/2. And so that's negative 1/27 for the first business. 4 to the 3/2 is the square root of 4 cubed. The square root of 4 is 2. 2 cubed is 8. So this is plus 8/27. So this turns out to be 7/27. And finally, we want the mean value. The mean value, again, is kind of like, not kind of like, actually, it's like it is the moment about the y-axis. Sometimes they call these moments in probability things, first and second moments, those sorts of things. If you remember, the way we did that was we slipped an x in front of our function. And then we evaluated it as wide as the function was, or as our interval was. Usually it's negative infinity to infinity, but remember our function is only defined as a non-zero value between 0 and 9. So what we'll do is we will look at mu, which is going to be the integral from 0 to 9. Now remember we have the 1/18 out front, and then it's multiplied by x times the square root of 9 minus x dx. Now there are a couple of different ways we could evaluate this integral. I'm going to do it by substitution. It could also be done by parts if you're interested in trying that. So I suggest you maybe try that for some extra integration practice. I'm going to use substitution, as I said. We'll let u be equal to the 9 minus x that's under the root. Du will be negative dx, which means the opposite of du will be dx. Again, we can change our limits of integration like we did in the previous slide. When x equals 0, u will be 9, and when x is 9, u equals 0. So here's the sticky part. The u, or the 9 minus x, that becomes u, and then the dx becomes negative du. What to do with the x that's out front? What we're going to do is we're going to take the u equals 9 minus x, and we'll rewrite that by adding x to both sides and subtracting u from both sides then. So x, the x that's there, is going to be 9 minus u. And so this will become, now we've got to be careful we get everything here. I've got the negative from the dx, so we'll have that. I'm going to pull the 1/18 out in front. My integral changes from x equals 0 to u equals 9, and then from x equals 9 to u equals 0. So we're going to go from 9 to 0. And I've got the 1/18 factored out. X becomes 9 minus u. And then the square root of 9 minus x becomes u to the 1/2, the square root of u du. And I'm going to go ahead and acknowledge the negative and switch the limits of integration here. So we'll have 1/18 integral from 0 to 9. In order to evaluate this integral, we're going to have to distribute the u to the 1/2 through. And so we end up with 9, that's not a 9, 9u to the 1/2 minus u to the 3/2 power du. And this turns out to be, after doing all the calculations, 18/5. While I was recording, you may have heard a jingle or two. I promise you that Santa Claus has not arrived early. Instead, we had a guest today, Augie, my dog, who decided to jump up on the couch and start chewing on his bone while I was recording. This video started getting a little bit too long, and so there is a part 2 to the video where we wrap up integrations and probability, where we discuss the normal distribution. So look for that video, please.